statistical model in research. When we talk about statistical model, we are in fact talking about a mathematical equation that explains a phenomenon or outcome. So there's an outcome that we try to explain from a model, but the model can't explain everything. So there's an unexplained portion. That unexplained portion is called an error. Generally, we expect that the outcome has a normal distribution, and what we try to explain about the outcome from the model, that variable also has a normal distribution, and that unexplained portion, where there could be one or several factors or variables that are not included in the model, are also having a normal distribution. The outcome is generally depicted by a dependent variable, and the model has independent variables, and the error will have error variables. So the purpose of a statistical model is to use the variables of interest to explain the outcome and the strength of the relationship between independent variable or the variable of interest and the dependent variable or the outcome is depicted by a parameter. So parameter is the strength of the explanation provided by the variation in the independent variable on the variation in the dependent variable. So if we look at now the relationship between the independent variable and the dependent variable, in the model we expect that relationship follows a linear relationship. So both variables are normally distributed, and if we draw the y-axis with the dependent variable and the x-axis with the independent variable, any change in the independent variable is captured by the change in the dependent variable. And in the modeling, we think that this relationship is a linear relationship. So we capture that change by the mean of the independent variable or the average, and the average of the dependent variable or the mean before the change, and then the mean of the independent variable and mean of the dependent variable after the change. So if we connect the two lines, we connect them linearly because it's an underlying assumption that we make there's a linear relationship. But it is not always that in real life independent variable and dependent variable have a linear relationship for each change in the independent variable to each change in the dependent variable. Because we're trying to explain linearly the actual outcomes in relation to an independent variable, the actual dependent variable could not lie on the line itself. So what the line does is it explains. And any distance of the outcome from the line, if you draw it linearly downwards, that distance is what is not explained by the line or by the model. That distance for each outcome, when we add them up, that is called the error. We also make an underlying assumption that these errors, if we plot them, there will be very low errors, minus, that is below the line, and low errors above the line, and then many of those errors or the distances will lie closer to the line and will follow a bell-shaped curve, a normal curve. So the dependent variable, independent variable, and the collection of errors will follow a normal curve. So we can have relationships trending upwards, trending downwards, or the dependent variable does not change along with the independent variable, where it is horizontal relationship, and dependent variable keeps changing while independent variable doesn't change, which is the vertical line parallel to y. Or it could be that we draw the best line, best fit line, but still that the outcomes do not really follow linearity so much, but they are spread across at various places. A better fit line for such instances are a curvilinear line. But in the fundamental modeling, or the basics of modeling, we make an assumption that the relationship between dependent variable and independent variable are linear. So we talked about the errors. So errors are the distances of the outcome from the best fit line that is estimated from the sample. But sample is an estimation of the population. But actual population behavior on the actual population line, the best fit line for the population, may not be exactly the best fit line drawn by the sample. But what is visible for us is the best fit line that we can draw for the sample. So the distances, vertical distances of individual outcomes to the best fit line drawn by the sample are called residuals. So they are the known errors. We can measure them. On the other hand, the population best fit line is somewhat a mystery for us. But if we draw a best fit line between the actual outcome and the population best fit line, that distance is called the error. But in practice, what we measure is the residual, that is the known unexplained amount. But the distance between the sample best fit line and the population best fit line is the unknown unexplained amount. So there are two portions. Known unexplained amount, which is error, and then there's unknown unexplained amount, but the total unexplained amount is called the error. So how do we measure the residual? To measure the residual, we compute the outcome distances from the best fit line. That's step one. Because these outcome distances could be above and below, above is positive and below is negative. If we add them up as plus and minus, because they cancel out, to get around that issue, we square each distance and add them up. So step 2. But we want to find out what is the average distance or the mean of the best fit of the errors that are distributed around the best fit line. So what we do is we take that sum of the squared of distance and we divide that by the sample size, but because it is a sample, we divide by the sample size minus 1, which is called the degree of freedom. So the unexplained amount in a sample, in a statistical model, which is the residual, is the sum or squared of distances of the outcome divided by the degree of freedom in the sample. So let's take an example. Say there are distances plus and minus when we measure each outcome from the best fit line drawn from the sample. Then we square them up. Each of those distances to get around the minus, and so we can find out the total distances from all the outcomes. And after that, to find the average distance, because these outcomes are for the whole sample, we divide that by sample, because it's a sample size, or the number of observations in the sample, minus 1, which is the degree of freedom. So the mean unexplained amount or the average unexplained amount is what we get after such division. So that is step 3. For us, in statistics, we express the relationships and attributes using averages, the means. When we look at a relationship between dependent variable and independent variable, our focus is when the independent variable changes, when the average of the independent variable changes, how much of the average of the dependent variable changes. So similarly, so let's look at what happens if we draw a line, a linear line, to explain the relationship between independent variable and a dependent variable, the changes occurring between the two. If we draw anything that is not the best fit line, the best fit line is where we minimize the unexplained amount, maximize the explained amount by minimizing the distance of outcomes from the best fit line. But if we draw a line that does not minimize, then we are minimizing, decreasing the explained amount and increasing the unexplained amount. So the distances of the outcomes from such a line would be much greater. Unexplained amounts would be much greater. So in statistical modeling, when we draw such a linear line, we draw the best fit line, and that best fit line maximize the explanation through the model about the outcome, that is the relationship between the independent variable and the dependent variable, and minimizes the unexplained amount or the error.